Great, so this is the last lecture of the course. So what we'll do today is going to be different from all the lectures, right? So it's much more from, yeah.
So what are you doing next Tuesday?
No, I think the 11th is the last day, right? So this is only the lecture 18. The next week is all the study week.
Next week is presentations.
Oh yeah, presentations.
Okay, so that was changed. So we are doing presentations next
Yeah, because many will not be. We'll announce it today. We'll finalize it. So, but it'll be next week. Yeah. Yeah. So this will be the last lecture, So yeah, so I want to more hear from you what you thought about the course. You know, how do we try to sum up, right? We covered so many different concepts. So let's kind of try to go back, and so I want full participation from you here. So I really don't have like lectures here other than, do you want to get the, no, you can do full screen, right? You can still, oh, you can't play, oh, okay. Yeah, so Shaheen will try to make notes as you record, you know, kind of try to sum up. So let's, as a group, try to come up with a summary of what we thought were the most, you know, like I had 3 groups, maybe what were the most surprising things you learned in the class, right? What you know, obviously I think many of you had background in machine learning before you came to this course, but was there something surprising or something that stood out, right? And then the others would be like in terms of, were there still some missing pieces? I mean, we couldn't obviously cover everything in this class. There are parts that are missing, and how that would connect to maybe other courses in the, you know, at Caltech and elsewhere, and also anything else that you'd like to share. So let's try to sum up how this course came together. Right, so coming to like what do you think were the most, you know, let's kind of say both surprising and interesting, right? What stood out for you in terms of the different concepts you learned? I mean, you learned both the foundations and the theory, but you also, you know, I talked about different empirical, right, studies and what they have shown. So what do you think are things that stood out for you? Yeah.
I think the most interesting part was for me, this discussion about the bias variance curve.
Yeah. And why was that?
I never really thought about it in that, like, you always see the traditional bias variance curve and try to reason about it based on that. And then suddenly there's like this new world emerging, and which is, yeah, which we can clearly see in the empirical cases, but at least I find it very hard to intuitively reason about what's going on in that regime, which is much easier in the traditional.
Yeah, I mean, and the jury is still out there on that, right? But I think the latest, some of the theory we covered was this work by Misha Belkin, Daniel Shu, and their students looking at how, you know, that you're having both this combination of like there's interpolation, so you're interpolating among all the training points, and at the same time you're trying to minimize the norm everywhere else, right? So there's still regularization happening, and the hypothesis is stochastic gradient descent and similar algorithms are doing that, but we still don't completely understand the mechanism of how SGD is achieving that, right? So that's still the gap, but at least there is kind of the intuition that going beyond the traditional VC bounds and looking at you know, solutions where I mean, in a sense, this is not entirely new. Like, so I didn't cover Peter Bartlett's work and some of the other works where they've also tried to look at the norm of the weights and try to give the bounds, right? And that's definitely tighter than having just parameter counting bound. But what's new here is in the over parameterized setting, can you get both interpolation and still the minimum norm, right? So that's the new part, I think. I mean, certainly if I were to pick, I would also pick that as one of the things that I was excited to cover in the class, because when I started to think about what is generalization, right? There is all the traditional theory for generalization. I could have done the whole course just on going into the depth of it, right? But I hope I gave you enough ingredients to understand what's a BVC bound and the Rademacher complexity, all these ways to measure complexity of a function class. But at the same time, how that's not complete for the cases we see today. Right, so I think the over-parameterized regime would be the case where there would be a lot of still open problems. So maybe we'll have one more slide of where, in addition to what we didn't cover in the class, maybe we can say what are the open problems and where do the big challenges lie. So we'll come back to that. What do you think, others?
The robustness by optimizing in a certain kind of near region, right, rather than the actual point.
Yeah.
So ideally we think that it could be good, but actually we see that it could hurt either the generalization or the accuracy. So I think that could be something very interesting to know.
Yeah. So what was surprising to you there?
Yeah. So originally we think that we augment data to a certain extent, because actually we do some augmentations data. We try to optimize in a certain near region so that we can play the Emacs game here. So we think that by doing so, we put in more computation power, something like that. So we are supposed to have either the better accuracy or the better generalization. But actually, we lose both of them, but only earn that one thing, that is, if we testing the same policy, then we could be a little bit better, but we still don't know whether it is better for the specific task or not.
Yeah.
So I think that's something interesting to know.
Right. So I think broadly what that opened up, right, we are always going after single objective optimization, so it's usually accuracy, we only optimize for that. And now if you try to bring in other measures, right, that trade-off is not at all clear, and most of the times there is no free lunch. You're now going after robustness. It could hurt your generalization, and it could hurt it quite badly depending on the scenario, right? Whereas, as you said, maybe one way of thinking is, you're augmenting your data by doing this perturbation. If you do it in an adversarial way, maybe that's an extreme form of data augmentation, right? Because you're picking like what is really the hard case for data and using that. But this worst case may not actually help the average case, right? So, and that's kind of this trade-off between worst and average cases that's really tricky, and that actually connects back to yesterday's lecture where we talked about fairness and bias, right? Like, we in machine learning, we go after averages if you're looking at accuracy, but now if each sample turns out to be a human being or something that's socially very important, right, then what are these other measures? And it's not going to be a free lunch, right? You're going to hurt in one measure to try to incorporate the other. And we'll come back to this. I think what's missing there is more of this multi-objective, right? We never frame it as a multi-objective optimization, and even what does it mean to trade off between the objectives, that's still pretty open. Now that's a great example. Like more people to participate.
With uncertainty, with like...
Could you speak up a little? Yeah, please.
Okay. So I thought it was interesting how some models they return like low uncertainty for regions where they have like barely any training data.
Yeah, the epistemic uncertainty, right? And these different notions of uncertainty. In machine learning, people don't try to decouple them. They don't distinguish where the uncertainty is coming from, and that could be a problem, right? Because some of it is just inherent, and there's, even with infinite data, you cannot overcome that. But others with more data could be overcome, right? And active learning tries to improve on the latter. If there is ways we can get more data and improve the uncertainty in a certain way, that's the kind of data you would like to collect, right? But if you can't measure this epistemic uncertainty very well, then active learning is not going to work well, right? So, and it's not going to work well if you, when we did the more careful experiments, if you recall, like I showed experiments from my collaborator Zach Lipton where he called it active learning without the crystal ball. Right, like if you are only given this limited chance, like you can't go back and look at all different choices of hyperparameters and pick the best one, right? If you're not given all that luxury, you're just given this one chance to go after the uncertain data to improve your model, then models that incorporate epistemic uncertainty were shown to be much better than softmax like classifiers, which were bad in terms of measuring the uncertainty well, right? So it is, for so many reasons, it's important to measure uncertainty correctly. And active learning was one of them, but the other one was going back to yesterday's lecture, right? For fairness and bias, if you especially present this to even if the human is making the end decision, but you're presenting that this model is giving a high confidence on this result, right? The human may then tend to go with the result because they think, oh, the model has 90% confidence, maybe this is okay after all, so they may not scrutinize the result if you also present a high confidence level. Right, and this issue is known as calibration, and so uncertainty quantification is a big field by itself. Andrew Stewart here thinks a lot about those issues. Trying to look at these different sources of uncertainty, and so there's extensive literature there. Again, if you're interested, you should certainly dig deeper into the resources for that.
This goes back to the optimization section. I found it surprising how symmetries and non-convex optimization maybe can be exploited or are not as bad a thing as they seem, given that a non-convex function might have lots of local minima. I still don't have a great intuition for how that can be exploited, but I thought it was a surprising observation.
Yeah, when you design these networks, you typically don't think of symmetries, right? That's most of the focus is on inductive bias, and that's important. But I think symmetries are also important. Like in one sense, you could say like now, even the global optima is now kind of expanded into big manifolds, right? It's no longer isolated points. You have manifolds of both global and local optima. But the question is how those, the landscape itself changes, it's unclear. Right, so symmetries are certainly making a difference, so that does. One thing we saw was the saddle point. Instead of, even if they're isolated, they become manifolds. But the same is true for local and global optima, right? So everything kind of is now continuous manifolds rather than single points. Whereas when we analyze optimization and any kind of results we have for non-convex optimization at the moment, assume like these isolated points, right? Like for instance, I showed the Nesterhaus result, or Ronks and their collaborators work on saddle point escaping through noisy SGD, right? So the analysis is much more tractable if you're assuming now there is this kind of a single point which is the optimal point or stable optimal point, and then there is a basin around it. And we don't have enough good tools to analyze when there are these manifolds, right? There's some beginning work on estimating on a manifold, but there you're trying to be on the manifold, right? That's a constraint. So this is different. So I think that's still open on what it does. I think for generalization, it could possibly help you, because now you have this global optima kind of have these big manifolds and big regions where instead of a single point, so it's much more stable to noise, right? So that's kind of, again, at the intuitive level, there is no good quantification of that. But yeah, I agree. There is almost no study of it in a formal way in optimization. Because for convex functions, they cannot have symmetries, right? So you have to go to non-convex functions to try to study them. And question is, what is even the simplest setting to do that? If you recall, I talked about finding the top singular vector or the eigenvector, right? That to me is one of the simplest non-convex problems to study. All the local optima are global, right? All the saddle points are in the space orthogonal to the top eigenvector, so you can characterize the full landscape. But then there are no symmetries there, right? So the way to think of symmetries there could be when there are now equal eigenvalues, right? So there's no gap, then it's a subspace rather than a single vector. And so now you can choose anything in that space. So there the analysis you can see is pretty much, it didn't matter that much whether it was just a single point or a space, but for general ones it's still unclear. But no, I agree, that's a great point.
So I find the idea of training a robust deep learning network is kind of interesting to fight against the adversarial attacks. Because because I'm doing some optical imaging experiments, so the data I collect are poisoned by Poisson noise or Gaussian noise all the time.
Yeah.
So I wouldn't have images that's clean as CFR10 or ImageNet data that we use. And so I find the idea of training a robust network is kind of interesting by maximize the loss given some adversarial attack. But one surprising thing is the generalization of networks isn't improved by the robustness.
Yes. Why do you think in your application adversarial way would be the way to go, right? If it's Poisson noise, you can still try to model it through the Poisson distribution and, use the appropriate loss according to that distribution, right?
Oh, yeah. So it's not only Poisson noise, but it's just a lot of aberrations of the images itself. The image will be distorted and have Poisson Gaussian, so sometimes I don't have a mathematical form of the noise in my images. Yeah.
Got it. So because you don't have a good specification, and that was kind of our, even with the GANs, which I didn't cover, which I assume Yisong will cover in the next quarter, right? It's all based because you don't know what the loss is, right? So this min-max allows you to figure out what the loss is. But the question is should you really go after the worst case, or is there another way to try to figure out what this loss function, right? That's still unclear.
One interesting part for me is how to collect data, and build data set is also very important. For example, the way we build ImageNet will include something like bias into it. And the CFR10 do not have a good test set. Something like that is, I didn't think of that.
No, I'm glad somebody would bring that up, because I thought I kept insisting in every lecture to try to think about it, right? So I know it's hard to do it, especially in a grad school setting, because this requires resources. This requires maybe trying to get onto Mechanical Turk and getting people to label, right? But if any of you are interested in taking on such a project, I can arrange the resources. So I encourage you to think about how to not just go collect data, but how to do it in a more scientific way, right? What is the scientific approach to formulating the problem of data collection, right? Like just as you would say algorithms, these are the steps, can you think more in a foundational sense how to do that? And then if you really want to do it and try it out, if resources are, and that's a general thing, right? So if you both compute data, these are constraints, feel free to approach any of us, me, Song, any of the faculty, right? So that I hope will not be the constraint. And so that's why I was focusing a lot on data, because that's where I think a lot of big open problems are still there.
Something I struggled with during the course was how words seem to be used in a different way in machine learning than they are in real life.
Can you give an example?
Adversarial. And adversarial, to me, it always means somebody taking an action against something else. But as you went through the course, you started out that way, but it then could be noise in the data, for example, that nobody had consciously gone in, if I understand it properly. Am I still not?
No. I mean, the adversarial need not be an actual agent, right? It is because you don't know the distribution, like I was saying earlier. then you kind of go for the worst case because you don't know, right? So, and that's, and also I think the other difference when I talked about this competitive optimization like GAN, right, that this is not, in economics, usually the players are like rational agents, right? They don't share their information, they have some private utility function. But this is a very different setting because everything's centralized, at least to begin with. The simple cases where you're training both the generator and discriminator. They still try to compete each other, but you have the freedom to tweak them, right? They're not separate agents, and I think that's a good place to start before we can even put additional constraints on how much information they share with each other, right? That creates, I think, additional issues. And in economics, people always think about best response kind of dynamics because rational agents want the best, right? So they're selfish agents. But that's not true when we are training these systems.
Right, so when you start talking about it, I would have one sort of view, and as time went on, it evolved.
Yeah.
Bias is another one. Where bias means something very different to you than I think what it means in machine learning. I'm still not too sure what it means.
So what do you think it means?
When I do a satellite data, we look at the sea surface temperature, it will come out, and there will be a bias. We have a control. We know what the mean sea surface temperature is, and on average, it's off by 0.5 Kelvin or something. And then there's a variance about that. But that doesn't seem to be the way you're using bias here.
So when I did the statistics, right, like I did the bias variance trade-off, that's still the same definition, right? Whereas in the previous lecture, when I was talking about fairness, I interchanged that with bias. And that's kind of, again, a different community that deals with, right? So their bias tends to mean societal bias. But that's only the two, I think that only the last lecture I started using it in that form, right? And I mean, when I say, and so people tend to throw around bias to mean like more, there's some underlying societal bias that created some unbalanced data or, things that's undesirable, right? So that's a more kind of colloquial use, but I agree, there is confusion because statisticians like to use bias in a certain definite way.
It's even a little more than that because in definitions on the network, if you look at a definition for bias related to machine learning, it says a high bias means the prediction will be inaccurate. When I think of it, I think of what the bias is. It's a single number. It's not that it will be inaccurate, but there is a number and I know what it is.
I mean, it's still a number, but yes, high bias also leads to inaccurate prediction, right? I mean, there's always a trade-off between the two, right? The bias and variance.
But if it's inaccurate, that's part of the accuracy, not the bias. I looked at it, but I might probably all things.
I mean, the mean square error is broken down into two terms, right? The bias and the variance, right? So if you think from that direction, then because the error relates to the bias, right? So that's the connection.
Anyway, those are things that I struggle with, that terminology.
Yeah, so I try to kind of say what it means in different communities, right? But yeah, I agree. There is, in the field, many things are thrown around. So, I mean, for a statistician, bias is this kind of an expectation, right? What is your estimator? How does it how far is it from the true underlying parameter, right? Whereas for, when people are talking about fairness, it usually means societal bias. So usually those are the two usages at least I've tried to have in the class. Okay.
So I found, again, on the visualization side, a little thing I found that's interesting, like this categorization, so that derives of more general, sort of optimizers by solving certain localized models with respect to certain regularizations on the local steps. And the other thing was to use sort of the spectral problems, both matrix and tensors, as sort of model problems of non-complex problems where things nevertheless go remarkably well, which I think is also a bit like the idea of extending this with like back in paper, which even goes with that.
So why do you think that was surprising?
I mean,
or like kind of what was your earlier view and what changed from that?
So I think what's interesting is just because, again, like we see empirically that many of the non-complex problems that we care about seem to be much better behaved than we can expect. and then at least we have one class where there's a simple mathematical structure that also in terms of the problems that they apply to is somehow similar to many of these non-convex problems that we're interested in, where we have a more concrete idea of why things go well. And that I guess it's interesting if you use this as a model problem to maybe study why more non-convex problems might be nicer than they go.
Right. And ultimately even, design like architectures or setups so that the non-convex problems become easier, right? I mean, we are kind of doing that more as an art than a science. Like, why should networks, why should you choose these hyperparameters? Why should this be the setup? And so that could guide us there to do kind of better settings so that non-convex problems become easy at the outset rather than having many people try out and burn a lot of compute to get there. What do you think? Anything else? People who still didn't participate, I'd like everybody to try to participate in this class.
We have some complexity results regarding the amount of data required to learn a specific task. And the interesting part is that for the deep learning, those ones really do not apply directly. So where you have somehow a limited number of the data, you can still do well if you use deep neural networks.
Yeah, I guess that's the over-parameterized setting, right? So, and also and that's because there's some regularization that's happening with the algorithm itself, like SGD, and so that there's a lot of interesting questions there.
Sort of going back to like the robust deep learning and like the adversarial training. I thought it was sort of one thing that I found interesting was there was that image that was shown for like the gradient visualizations in the adversarial training in the normal case. And I found it sort of puzzling that we weren't even interested in the fact that like the adversarial training provided so much more application in like the places that we were interested in, but we're still mainly focused on the average case and the fact that like we don't want to really pick up those visual or like those. It just seems more complicated and doing more sophisticated things, but we're not even interested in that in the deep learning. Or maybe not so much that we're not interested in it, but we're more interested in the average case.
Yeah. I guess that's a good point, right? Like, robust deep learning, at least in some cases we've seen in the gradient maps that tend to be more interpretable. The challenge is how do you measure this? I mean, accuracy is easy to measure. So you want somebody like looking at each image and trying to assess, okay, was this kind of the right region to focus? Or even like, even if you label that region, right, how do you measure like the mismatch? Because it's not a definite thing. I mean, it's not, and that's why it becomes more challenging, right? I mean, people I think have tried to do it in cases where they took like Microsoft Coco or other data sets where there are semantic segmentation available, but they only did like image classification, and then they tried to see the gradient map and saw, because there's the ground truth boxes. So people are trying to get those kind of other surrogate measures for interpretability, but it's harder, right? I mean, and this is again not a justification, right? Especially when it kind of comes to the lecture from yesterday where we looked at how it could amplify societal biases, that simple objective functions tend to do that, right, like accuracy. But on the other hand, machine learning people like to start somewhere from where they can build all the algorithms to achieve that objective. And that's where I think it goes back to, again, how do we think of multi-objective optimization? In optimization literature, there's some work on that, right? There's not a lot. I mean, most of it is like kind of looking at like trying to, be able to get any convex combination of objectives, you should be able to optimize, right? So you should already have a procedure in place so that on the fly you could do that. So people have, developed theories like that, but very little of it has come to machine learning. I think that's where we should probably be thinking about those more.
I sort of have a question related to that as well. So for interpretability, we saw those images, but are there any other ways to measure interpretability? Because the way that we were sort of comparing the two cases of adversarial training were one was like in the where the training set had no adversarial entity, so it wasn't really a fair comparison. So I'm sort of wondering like what are good ways to compare whether like an adversarial training is seeing something more sophisticated.
Yeah, so interpretability is something we missed in this class, right? So that'll come to the next one too. And it's still very unclear, right? So people have like measures like, as I said, if they have some other ground truth, they try to say, does the region correlate with what they think should be the region, right? To make the decision. That's one way. The other is, depends on the application. You have some underlying, this is the ground truth, some causal modeling, like, this smoking causes cancer, as a simple example, right? You know this underlying pathway of causal mechanisms, and now you try to see a model without being given the ability to causal inference, can it kind of get to that closer than otherwise, right? But there's no universal answer, and that's why it's much harder. It's so application dependent that at the moment we don't have general purpose ways to define it, right? And maybe there isn't a general purpose way to do it, and that's when then people laying the foundation have trouble because they like generality, and so those that are not amenable to that, those concepts tend to suffer a lot more, right? It takes longer for the field to grapple with that. Any others?
It's like in the vein of having a good training set, that one example you had of like changing one training example and the impact that that was like, that was pretty surprising to me that one example could have that action. I was waiting to the slides so I could read that paper, because you want to hope that like if you have large n number of training data that like any one is not that important overall.
Yeah.
And the idea that certain things can influence as like greatly disproportional is like counterintuitive, I guess.
Yeah, for the stability bounds, right? That's kind of the extreme thing, is when just one example could grossly influence the outcome, right? So that's like the extreme. I mean, and so it's like that's where in a way like maybe then we are being looking at extreme cases helps us then bound the other cases too, right? It's not clear if, in some cases that's then okay, but in others maybe you want to go for weaker measures, right? Because that's an extreme one. But that's where for theory it becomes a lot more amenable, because you can easily analyze what is the impact of one sample. Anybody else? No? It's your last chance for this slide. Okay, so let's go to the next one. What do you think we already answered some of this, right? You can write that down. I think the interpretability, we don't have very good answers. We kind of didn't really get into it much in this course. And that's where, when Frederick Eberhard teaches causal inference, right, I think that's probably the best answer, right? But it just may not be possible in every application to be able to get enough information to do causal inference. I think that's where at least I see it. And then what are the intermediate results you can get if you can't get to the full kind of, the ability to reason about not just correlation, but causation as well. So what are the others we missed?
So I think in terms of the application examples, I found the distribution was sort of a bit skewed in the same way which the distribution of application examples in machine learning is skewed in general. So it might be interesting to, because there's particularly for many people here that have, for example, physical science background,
yes,
it might be interesting to try to cover some of these, even though if you pick at random some machine learning paper, chances are they are about videos and
yes, a lot of cats and dogs. No, but that's a good point, and that's where more broadly the AI for Science workshops we are organizing are trying to do that, right? And also there are far less number of examples of going beyond the standard data sets, right? And that comes back to the other aspect of how do we get the good data, how do we get like the domain knowledge, and so I agree. I would like to increase that too, and that's where, more pointers we can get on that, right? So that'll help us for the next time I do it. So do send pointers to other resources there.
Maybe something about reinforcement learning.
Yeah, so I completely missed reinforcement learning. Again, Isong did that, I guess, last year, right? So, and so that's why, again, this is one of like trying to optimize for coverage across all the courses. So I agree, but hopefully we'll get back to that in one of the topics courses.
So we talked about uncertainty in active learning, but because our group is working on active learning project for this course, but we also want to know the likelihood of our data. So but we found like from a paper, like all the current, I think it's still open problem. So if you train like, let's say on MNIST, the digits, but then the network will also think the digits of 1 has a higher likelihood than others. Mm-hmm. Yeah, no matter what our training data is. So it's because like the mean of the distribution is the same and the variance of 1 might be smaller. So it always gives a higher likelihood to 1. So is there any way to generate a reliable likelihood for the data?
Yeah, no, that's a good point, right? And that kind of goes back to generative models, which I made a conscious decision to, I had 2 lectures and I removed that when I realized Isong is gonna do a full course on that, so hopefully he'll address the issues there. But yeah, that's a good point. I think all these are really important ingredients with machine learning, right? But we can't cover everything in the course. But it's good to make the list so, we also know where the gaps are, and if there are other courses, then you know where that is, right? Otherwise, you can go on your own and explore this. What do you think?
Yeah, so based on the syllabus, there should be a part of the generative model. I think. Yeah, so I mentioned the likelihood is something encoded that part because maybe it's very similar to a cross project. I'm doing the generative model using the GAN. Yeah. So sometimes, because when training this model, we can not directly measure the loss, either the discriminate and generate to some extent. Visually, they are kind of locked in a certain way, but actually we want them to gradually improve. So, but now I have very little knowledge about that part. So I'm not quite sure whether in this part, with this progress, are the 2 models actually improving? Do we have any sign so that we can measure the quality, whether something goes to better or something goes to worse? Because they're kind of fighting with each other. We don't know whether one part of goes good or bad. And also, sometimes when we want to throw them apart and use one part, will that help? Maybe something, I was thinking about.
Yeah, I mean, that's a good point, right? So, as I said, I changed that plan later in the course when Isong announced that he would be doing generative models, because if there's a full course, then I felt like, whatever I compress in 1 or 2 lectures will not cut that. And when it comes to GANs especially, it's not a likelihood-based model, right? So how do you even measure the performance of GAN? If the GAN doing well, is it really training? Should you stop? All these are still open, right? So there are really no great answers, and that's where in the competitive optimization lecture I try to address at least the oscillation issue, right? So if you're just doing blindly simultaneous gradient steps, right, that will tend to oscillate even in a simple bilinear game, right? So that kind of gave some window to it. But yeah, the questions you asked are in fact very open. And so that's what with generative models, there's the traditional likelihood-based models and then the likelihood-free models. And the thinking and the tools are very different in the 2 as well. So that's an additional source of challenge. But yeah.
And also, there is one thing we mentioned that is called lifelong learning.
Yes.
I think that is something maybe new to me. So so I'm not quite sure.
Yeah. So lifelong learning again related to reinforcement learning, right? In the sense you're in both of these, you're thinking of non-stationary phenomenon, like it's phenomena keep changing, and so I had to make choices. But I agree, since it related to reinforcement learning, I decided we could kind of table that to another topics course where that cluster could be addressed.
One thing I say in general, we can look at papers and see the good results they have at the end. But I think it's also very valuable to try to pull out what were the tricks and what were the specific things they needed to do to get that paper to work. Because odds are it didn't work the first time.
Yes.
And by glossing over that, it's you can what's possible, but it's very hard to actually do things without just go back and rereading everything all over again, because building a repertoire of strategies that have worked in the past is very useful when you are trying to tackle a new problem.
Yeah. I mean, it's a trade-off, right, on whether, in this course I wanted to kind of also cover the breadth. I mentioned that in the first class, right, because we have, Yi-Song's course and then my course, and, Yasu's course is much more geared towards beginning undergrads, right? So given this, how do we cover, and at the same time, right, so, and that's where I said, we won't be able to go into too much depth on each one. But I do agree there are a lot of tricks, and the question is, in the foundations course, I wanted to focus on the concepts, right? So that's where I wanted to at least give enough theoretical grounding to get you to think about this. And when it comes to specific tricks of the paper, it's not even clear what worked, right? And it's not clear to easily how we can glean it without actually rerunning the experiments. And so that's something hard to teach in a class. But I agree, it's important, but I don't have an answer of how I would be covering that. Gil.
And so for one example, for the example of GAMs, I think we mentioned you need, it's a balancing act, and you need to make sure that the balance between the two sides is not disproportionate. And so in practice, if you've been working on GANs, you've probably found yourself in a situation at least one time where there was an inequity, and either the discriminator was useless, or it just killed everything, and the generator was dead.
Right.
And you don't need to have a theory, because there's no theory, but empirical examples of in our lab, in our research, we found that this can work sometimes.
Yeah, no, that's a good point. More negative results, right? So certainly, I think, and that's kind of the bias of the field as well, right? In the way we publish papers, we tend to hide all this, and that's creating these blind spots for especially new people coming into the field, right? Reading the papers, you don't get that knowledge. And so that's a great feedback. I'll definitely try to incorporate that more in the next iteration. Anything else? Yeah.
So maybe not for this course specifically, but maybe across coursework here, I find that for application-based deep learning, there's not a lot of coverage in the courses here. So that's, I sort of like that we sort of covered that towards the end in the problem sets. But in my opinion, it just seems there's a lot of applications that we could try and look into that are not really from CFAR 10 or Anima or something, things that we're conventionally looking at.
And that kind of goes back to Florian's comment, right? And it's a chicken and egg problem, because there isn't a lot of it, but now as more of it is, machine learning is expanding to other fields, and especially here at Caltech, we have more of the kind of personal connections to look at the ongoing projects, right? There could be more. I'll certainly make it priority to bring more of that in the next iteration.
Sometimes there's some merit in, for example, presenting a technique based on whatever was the first paper introducing it, to use the example slide. But on the other hand, typically the first paper is introducing things that will focus on these very standard examples, because they show everyone, we did it so great, and something that we tried as well. So it might really be something for the future lectures to try to say, okay, we mentioned whatever was the first work, but then we still choose maybe one of the later application works in a more interesting domain, in order to mix things up a bit.
Right. Right, I agree. And it's again a balancing act, right? Because I wanted to give enough foundation. I mean, the title is foundation, and I know some students wanted like a very strong theoretical backing, and it's important too, right? Like having that theoretical grounding. And so I try to mix it, and I think we can like kind of make the empirical part as well more grounded, I would say, like in terms of, but the field is evolving so fast, it's hard to do that, right? Because some of the papers are just literally a month old. And so there hasn't been a lot of scrutiny and a lot of, so one could be like more like a timeline of what people thought was happening and what didn't, what did the latest paper. So, I think it was in robust learning, right? I think there was a slide by Zico Coulter who tried to give that timeline, right? So there's a bit of that back and forth, but that also makes it more a confusing message, right? Because then you don't know what's going on, and maybe that's where the field is today.
Yeah, so one of the things I struggled with, which really came as a surprise to me, was the number of different learning algorithms there are. So I just Googled what types of algorithms are, and they came up with 27 types. It would have been really useful, I think, early on in the class to sort of structure it and say, here are sort of classes, sort of like a tree of life or something.
Yeah.
Species. And these guys fall over here, these guys fall over here. When we talk about this is the main focus.
Yeah.
Because as somebody wants to use it, I still don't know which algorithm I should be going with.
And sometimes it's not clear, right, what the choice of algorithm is, and that kind of, it's almost like this hyperparameter, like what do you choose? And I agree, this is the most advanced machine learning course at Caltech, right, a general one, not the special topics. And so I assume like kind of, and I told that in the first lecture that, so that is, again, the choices I made. But I will try to, in the first lecture, I tried to give some of it, but maybe I'll kind of try to give like an extensive survey or something to begin to ground the concepts and then go to the details.
Yeah, for example, in Nisan's class, he sort of has how you go through it on a machine learning example, all the elements, and you keep coming back to that.
Right.
If there had been something in the beginning of this class, it's like here are the classes of algorithms, and come back to it and say, today we're going to be talking about this.
That's a good idea, yeah, to kind of have one running example to different lectures.
Sort of structure.
Yeah.
I mean, I need a decision tree. It would be great if there was a machine learning program and I could just give it in English what I want to do, and it would come back and say, you need to use this algorithm.
Right. Yeah, I'll think about it. I think the concepts I covered were so broad, it's hard to have like maybe one example, but maybe one kind of group of examples or something, right? Or connect to the earlier ones. I'll definitely take that into account. Yeah.
Actually, I would enjoy if you were able to talk more about the decision trees in general, just because at the last part, the logic-based modules seem to be very related to it.
Yeah.
So if there would be, I guess, more of that.
Right. Yeah, so I guess more broadly, like blending classical ML and deep learning, right? Like how do all these different concepts relate to one another? I agree. This course was heavily deep learning based, right? But that's where also many of the recent developments have happened. But I agree, that doesn't mean the others are not important. Especially, maybe that's a good way of connecting. I could have used the lecture where I tried to argue both about symbolic reasoning as well as representational learning as a way to bring that in. Yeah, that's a good point. Anybody else? No one wanted to see causal inference? Sorry, go ahead. I assume.
One thing, like when we talk about like making larger and larger models and like the different regime of training, I think it might be useful just to give some grounding into when we say big, how big do we mean, and like just like a quick summary of like recent advances in computing with like GPUs and TPUs, and just a sense of like how big does this big mean? And like when we say that it's using a lot of compute resources, like what is that?
So if you saw like in those slides, right, which I borrowed from BenRect, there was like the P by N ratios, like how many parameters to how many number of samples. So that was a notion of like big. And with the compute, again, like how many cores and like, there were some plots there. So I kind of alluded to that, but yeah, I went through that quickly in the, kind of, yes, I could have spent a bit more time there. But yeah, I agree. Thank you.
And maybe not for this course, but something we're also very interested in is time sequence dependent models like natural language processing, something like that, because now it seems to be more focusing on the 2D information, but when we move to videos, speeches, but maybe for the whole university. To some extent, at least.
I agree, more like sequence models, we also missed that.
Related to that, I think it would be useful to touch on like things like autoencoders and embeddings as a way to reduce the complexity.
Yeah, and that's kind of related to generative models, right? So I assumed, kind of, left it for Isong to cover that part.
So you brought up causal inference, and I was wondering if you could comment a little bit on what there is to causal inference at the moment beyond like Bayesian networks. Like, does the field of causal inference have more to it, or when we talk about causal inference in machine learning, are we talking about learning some sort of causal model in formally directed?
I think there's just so many open problems. I don't know if you had the chance to come to Caroline's talk. Caroline Euler, so she gave a great summary of, I think, where the latest things are and what the open problems are, right? So one direction is, here we are assuming there's some fixed data and you're trying to do causal inference, and many times it's just not enough, right? You just cannot identify whether the link goes this way or this way. But you can do interventions, right? And now there's the whole literature on adaptive testing and how many tests to run, right? Like in the classical literature, but the two don't talk to one another. So the question of what is the kind of interventions that's feasible to do, right? There are constraints, you can't do all interventions. So what's the ones that is feasible, and then how do you optimize for that? And how do you get the most information, right? So that relates to like active learning, these adaptive testing, all these concepts, but involve like inference of causality, right? So I think that's a big open area. There's a lot to be done. And another one is combining like, the other aspects like like trying to figure out if these are latent effects or causal effects, right? Like, because, there could be like a common latent variable that affecting both, right? So how do you test for these kind of, and maybe you want to learn about that latent variable, right? So not just kind of rule out that this is a causal link or not. And that kind of relates to some of the earlier things I talked about with tensor methods, right? How we can use to learn with latent variable models. And there's no causal reasoning. So can you have like those hybrid? I think that's an open problem. And the third would be like these representation learning with causal inference, right? I mean, all this causal inference is great, but that happens at the level of concepts. You already pin down to a few concepts and a few hypotheses. You're trying to reason about that. But how do you get that from continuous data? Right, and it's usually human engineered in small systems. Humans can say, oh, these are the important concepts. Let me now try to learn the relationship. But with images, how do we like extract from these image space to concept space, right? Like if it's a few number of categories, you can just do that. But maybe there's better concepts than just those categories, right? I think going from that representational learning and then doing causal inference on top is also very interesting.
So if I understand what you're saying that rather than kind of collecting the variables in our model by hand and saying this is our hypothesis for what the causal structure of this process is, we can try to learn that without kind of any a priori knowledge about how many factors there might be or
I mean, you could use some of those as domain knowledge rather than hard code just there, right? So, because you could even be wrong, right? Maybe those are not the only, they may not be the best concepts to explain the graph, right? The graph may be too highly connected if you go it at that level, but at some level you could have a sparser graph representing the same.
So what applications would that be, do people think that's even useful in? Because it seems like it's kind of counter to the other strain of machine learning, which is we should restrict our machine learning black box to as small a region of the problem as possible, for example, in these kind of physical applications where, like every talk I go to, it's like, well, we impose as much structure and physical laws on the problem as possible, then do machine learning for the unknown dynamics or something. But what this is suggesting is that we're putting a black box around our entire causal process.
It doesn't have to be these extremes, right? I mean, there's these two extremes, and what is that middle ground is what would make it practical, right? Like,
sure, so I was kind of wondering what applications would be appropriate for this.
I mean, for instance, if you think about like now vision-based control as an example, right, to ground this. So now you're going from these images to control, right? And this is still hard because there's so much. First of all, you need it to be robust, like just a few pixels changing, you don't want that to change. But you also want to like try to track the temporal dynamics and reason about what's happening, especially if there are a lot of interacting objects, or think about like car driving, right? You want to like kind of, I mean, humans will be doing causal inference when they're driving, right? Even in an unconscious way. But how do you get that to, right now the systems don't do that, right? So how do you go from that perception module to a causal reasoning system, as one example, right? And the other could be like from all these like kind of data on like kind of different kind of tests you do on molecules or drugs, and finally you want to test, like currently people only go with one hypothesis, but maybe you want to like, learn like what the, how the sequential processing will evolve and what should be the concepts to track, right? So, I mean, you can always hand code it to a small number of them, but maybe there are others, right? I mean, in this kind of car scene, right, unless you know the environment beforehand, there's only going to be this number of cars, or put some upper bound, or say like only these kind of trees will occur, right? If you just try to do it in the wild, you don't know what those concepts are. And so it's more flexible, right? So if you knew all the concepts to ground, you're done, right? You don't need it. But if you don't know that, and if you think there are meta concepts that could better summarize and kind of better reason about, right, we should rather be having the flexibility in the model to do that. Anything else? What else do you think we should talk about? I think the third one is just like general comments, things, anything else you'd like to?
Don't make people grade each other's homeworks.
Okay, I'll take that into account. That, I have to admit, this was an experiment, and I was told that at Caltech people are open to experiments. So it's certainly, you are the guinea pigs. I hope you don't hold that too much against me. But this is the first time I'm teaching. I wanted to, we'll certainly take that into account. But why do you think that was a bad idea?
Well, that was the reason I decided to drop the course, but just hang around.
But why? It was a lot.
Excessive work, and I saw comments like people couldn't get each other's code running. It didn't sound fun.
But I mean, for those who were taking the course, I think ultimately those were addressed, right? Like you could get, or
I can speak for myself and a few others that I've talked to about this. I think the main complaint is that many of us are in graduate school, and like even those that are not. So when we do something, we really want to have it be for our own learning, but we didn't feel that we learned from the peer grading experiment. So the main learning that goes on happens when we're wrestling with the problems and we talk to each other when we're working on the problem. So that's when the learning is seeing someone else's solution and then assigning what sort of feels like an arbitrary score. I don't know, there was kind of, for me, there was zero learning.
Okay, that's good to know.
Yeah, to show that, particularly because many of these questions were very open-ended. So, I mean, having been a TA, I think one has a much better, first of all, I mean, I mean, it's somewhat easier to grade and give helpful feedback on these problems if one is grading the entire batch on this problem and one has a more overview. Whereas, like if you get like you have these very open-ended problems, and then you get three things that are completely different from like the official solution or from anything else, and you don't have enough time to invest to try to, I mean, like do your own research onto each of these solutions, then probably the feedback that you will give to the students will be much worse than the feedback that the TA that sort of does this for a living.
Yeah, but even the TAs are not really doing it for a living, right? That's the problem. But also, I think that's where I hoped, like, because it was open-ended and because this was like a graduate course, I hope, like, people are not really trying to game the system rather than to, like you're seeing like what others have a perspective on this open-ended question, right? That's what I was hoping would be the learning. But yeah, I'll see how we can try to improve that or try to just go back to the traditional grading.
I think I would much enjoy if the homeworks were more structured, like a series of Kaggle competitions, like one of what Nissan did for some of the problem sets.
So my philosophy is not to do leaderboard chasing in where, that's kind of what I was saying in this course, not to do that, right? And it's much harder to say go collect good data or things like I would really like to see. It's hard to do that in an assignment level. And so that was the reason. I mean, I only gave that one like CFAR 10 experiment, just kind of, I feel like that's the minimum bar for anybody today doing machine learning, even a hardcore theorist, to be able to do something like that, right? So that's kind of the only reason I stayed away, because I felt like at this kind of, at least in this kind of an advanced course, the hope is most people have already kind of gone past that and want to focus on deeper problems. I mean, they're easy to grade, but kind of that was the goal, like, to have more of the open-ended one so that I hope people would be more creative about it.
It was definitely more fun to work as a team, solving a problem.
Yeah, so I could allow for teams the next time for assignments too. Maybe that will make it easier, and maybe the peer grading is also then like different teams exchange each other, so all the load gets reduced. Maybe.
Even if it's like not like a leaderboard thing, I think that like finding other, I guess I already said this, but like finding other applications like the time series thing or like any other application, I feel like people will get a lot more out of it, because for like the CFAR 10 thing, once one like increased the capacity of the model and then ran it on the GPU, it sort of just worked, at least in my experience. So like I think finding like a more interesting place where you could like sort of think about it more critically would be.
Yeah. And that's where I was having kind of a trouble, right? Because this course was meant to be much more theoretical than Isong's course, right? That was kind of the division of like kind of in some sense. So that's what it was pitched to be, completely theoretical. And I wanted to deviate from that, so I did only smaller deviations. And if we are trying to do bigger deviations, I have to rethink, right? It's because then what I want to do what Isong is not covering, right? Otherwise, we don't want to repeat the same, and that's trickier.
Yeah, I think it's good to know some theoretical derivation, something like that. But maybe next time we can put it on the slides rather than on the board, because the board is very difficult to see because it lines for everything and sometimes out of the ink. So we try very hard to see what's happening on the board.
Maybe I'll try to use one of these like iPads and write it there on the board, because I don't want to like write it as we go, because there's some, at least for the theoretical concepts, I tend to learn better when I do that. I don't know about you, right? If it's already there in the slides, tend to be more passive. But for these other application ones, that's the easy one, because you're showing figures, you're showing like plots, right? So theory, I didn't want to do it, but maybe I'll try to make it so that it's easy to see. All I'll try to write big.
Regarding keeping the homework, so I would say that the ones I enjoyed the most were actually the ones where one had a bit of a coding portion. For example, the one on the sign SGD. I think more homeworks like that force you to go into some interesting paper, and maybe just to get a better feel for how these things work. We code something, because my impression is that even if these, so I mean, maybe I should have also taken these ones before, so I didn't do that. But also besides that, my impression is that for many of these things, right, it's not theoretically very well understood anyways why these methods work. So I feel like one gets a better idea for that when one plays around with code, rather than one does like the typical symbolic manipulation thing that still doesn't really seem to capture necessarily that much of why these methods work. So these two, like this C510 and this science GE, almost I found interesting, and I think it would be nice to have more of those.
Yeah, along those same lines, like if you're trying to structure assignments for theory, I feel like two big paradigms you could do is you could do something like creating more theory, which was kind of like what that assignment was. That was like just reading papers and like returning back what they said. Or then there's like trying to apply theory and like build some intuition, kind of like the science GD thing. I think, at least for me personally, I find the latter far more like rewarding. And I think you could definitely make other things like that of, for example, like make a GAN, and you get provided some like tests, like you get provided some like initial code, and then it's like see what happens when you play with this. So you don't have to. It's not like that as time intensive as starting something from scratch, and it lets someone explore the space of applying what we've learned to see actual changes in performance.
Yeah. That's really good to know, and that's where probably I even miscalculated, because many other feedback and talking to faculty, I think the plan was to have a purely theoretical course on machine learning, right? Because that was missing here at Caltech. And I tried to deviate, and I was hesitant to see how much deviation we could do the first time. And I was hesitant to see how many people would be open to kind of more coding assignments, because maybe they really wanted to learn theory here, right? So that's where, I was coming in blind. So it's good to know that if you're open to more coding, I could have easily expanded that, but we made a conscious decision to go more into theory, and some of it is needed, but I think we'll try to balance it better.
So I believe the discussion about tensors seems to be disconnected from the rest of the course. So we didn't really have good applications of tensors, for example, like hidden Markov models. We didn't cover that.
Yeah.
So maybe there can be a more deep discussion of tensors and their applications.
Yeah. So by the way, next quarter there's going to be a special course on tensors. So Richard, who is a postdoc with Joel Trop, and I think John Preskill is doing both from the classical perspective as well as the quantum perspective, and he's consulting with me and others to see how much of even from machine learning perspective we can add, and that was kind of also the idea of this course, right? To give you at least the overview that these topics are there and some quick summary, and then hopefully many special topics courses you can dive deeper if that's your interest. Yeah.
Going back to the homework and the open-ended problems, I actually thought it was more interesting to do peer grading on the open-ended problems than on the other ones.
That's good to know.
Because for the other ones, you kind of just look at the answer at the end and you just kind of read through it and it's all the same. But for the open-ended ones, it's more interesting to see how other people approach the problem.
So was there something surprising that leaped out when you did this grading? Did people think differently from what you had, or?
Yeah, I guess for the Sinus GD one, I saw a lot of different plots from my own plots, so I thought that was pretty interesting.
Okay, good. That was what I was hoping for. So at least somebody found that. Yeah.
Actually, I'll be teaching a course next year at my institution. A lot of students in it. I was going to use peer grading as well. So I was interested in the comments. I'd be interested if it's okay with you to hear what the TA has to say about it.
Oh yeah, what you have to say about peer grading. Sorry, we've been not.
No, okay. If I was a student, I will complain too. As a TA, I'm happy. Obviously, but I think I sort of agree that grading open-ended ones makes a little bit more sense than grading the one that just you read the answer and then just do the unnecessary word of TA thing. So I think maybe we can change it to that.
Yeah.
So I think it's because this is the first time this class has been taught in here, so gradually I think we will improve a little bit more.
Yeah.
But I don't know what comment you want me to make.
Well, Did you look at what the students, when they appeared?
Yes. Yes.
You looked at
we looked at like if there are any discrepancies or like if they took off extra like not good enough points. I mean more than they're supposed to. We kind of adjusted that too.
Right. So what's your sense on how well it worked?
Actually, it worked more or less nice. Like there are not huge gaps between the questions. But I don't know if it's because of the questions itself. Maybe it was more open-ended. There will be more discrepancies between the grades. Since most of the questions were like, the answers were clear. So the grading was more or less the same in each of the peer grades.
Yeah.
Yeah, in terms of peer grading, maybe we can also send the graders' feedback to the students. So that because now we only have points.
That's true. Yeah. But that's more work for you guys.
But because every time when I'm grading this one, I also write about 1 page per assignment, so to see what I try to code or what I'm thinking, what I need to correctly or not. I see. I'm also very happy to see when other people see my thing.
I think what I can add to that is maybe we can create a framework of peer grading instead of asking people to do individual ways of doing it, so that it will be at least more systematic if we want to go with peer grading. So I agree on that because it's right now we're not putting any template to follow. So I think giving a template, at least like for instance you were saying you're doing more than some other people, let's say, because some people just put a grade and then skip it. But some people like just put more effort on it, so I think we can balance it somehow.
But did you find it useful overall, or?
I think I'm pretty agree with her point. That is, especially on the experiments, and some maybe more application-based questions, which means we don't have to. We can see how others implement something, what they're thinking about some of the problem. I think that part is very happy to see the result. But on the other hand, that is, it's very difficult for us to deduct some points on this very open-ended one, because if anybody says, I found this one, I found that one, we say, oh, that's reasonable, and we can only mark the part. So there could be, it's good to see that, but maybe for the marking part, we are not. Some people think you are doing good. Maybe some people think you're not doing good. So, I'm pretty thinking that it's very good for us to see how to do that. But maybe for the grading, we may let one criteria to do so that the standard can be fixed. Otherwise, maybe some people think that you missed one step. I did like 30 points. Some people did that.
But it was always going back and checking the discrepancies, right? So we were still having the safeguard.
Make sure that nobody is getting any bad grades.
The biggest thing is the min-max problem. So every people when doing this grading, we try to not deduct too much because we know others will not deduct too much. So there's a safe range that is if we all give 93 points, then we will all good. So.
but that's the thing too, right? I mean, the goal of this kind of especially open-ended problems is not to really go after this last point and go really that kind of. It's more about like, did you get the concepts overall? And we can always kind of maybe next time have peer grading for these open-ended parts and more like kind of the fixed ones, like that could be like.
I don't care about the points too much. So I don't really care. Maybe I get 1 point more. So I'm happy to see other results, maybe experiment.
Okay, good to know.
So I think I'm pretty agree with the guy who mentioned that is maybe we can put home up to date because the costs tend to be high level. So maybe we can have some trial on some maybe not modern models or something like that. So. Especially more days, people are looking into the reproducibility, so that maybe most of them will post a code or something like that.
Yes.
So if we can have a guide that you were talking about maybe some topics that is again maybe we can have a framework like the C1st we have now, so we can have a hands-on, maybe not take too long, but we can actually try, maybe as at the last two sessions are doing, we can try to tune some models, add some tricks we learned to see how it affects the one. I think that would be useful, because I think it's to some extent difficult to completely pick out the theoretical part in the learning part, because now this region will to some extent rely on the experimental results or empirical experiences, so get some hands-on, I think that
I'm trying to balance that.
And also we didn't know how the coding level of the classes.
Yeah, and that was actually, we really limited the number of coding questions, right? Because I didn't know how many would want to be doing that, right? Because the course, when you say foundations, it means theory, right, typically. And so I've already deviated enough. So if there's enough like actually interest to do that, certainly we'll expand that. Yeah, sorry, you were probably,
I feel like a lot of the, like there, I think the open-ended questions, there's benefit to seeing other people's work. I feel like a lot of the benefits could be extracted by like having these types of questions that are like more like applying theory in creative ways and seeing what people come up with. But then instead of having us trying to grade, which is like very difficult, just like we submit and then you guys can pick out like good, interesting examples that seem to like have different perspectives. And then instead of us getting only 3 random ones, and like there's a good chance that like if half the class all did basically the same thing, that you grade several of those and look at it like 3 different perspectives, then you can, the TAs can grade, and you can like pick out particularly good ones from different examples. You can make sure they run, you can make sure everything works, and like share those with the whole class so that you can still get different perspectives, perhaps in a more reliable way, and you don't have the burden of having to grade.
Okay, you.
So I have a question about like, so for the content covered in this course, I've heard of like other traditional foundations of machine learning courses following another like textbook. Like I forget the names of the authors.
Yeah, like learning theory books, right? There's many, but so many of them are in the classical realm, right? Like as I said, like generalization itself, I could have done the whole course, or all the concentration bounds, the optimization part, right? So there are these courses that are purely theoretical, and I wanted to kind of expand on that. And any closing thoughts? I mean, so I know peer grading will certainly look into it, so I know that's gotten the signal that bothered a lot of you, so that's good to know. But anything else coming out of that? What else did we miss?
So like, I think we only have like recitations for like maybe like 3 times or something, so I think maybe we could have like some more recitations. So I think like we ended up missing maybe like some practical applications, which a lot of people mentioned. Maybe we could have like recitations with other those applications.
Yeah, well, so it sounds like more practical.
I don't know what section, more work to TA. That should be.
Yeah, by the way, that reminds me, there's a PyTorch workshop this Friday, right? You got the announcement for that?
It's already booked out since I think the day after or something.
Sorry, well, you can at least be on the wait list if you didn't sign up already. I didn't realize it's already booked out. But that's the other hope too, that if we have more of those engagements happening within the university, then there's enough of like the minimum levels that have, people have reached due to these workshops, and then we can kind of build up more in the courses. Great, so it was a pleasure teaching this, and yeah, if there's more feedback, do get back to us. So next week we will plan the presentations. I'll be remote, but we'll try to have like a remote video conference, so I do try to want to be participating.
So like, we had like, for the first round of reading, we had like a template and like clear ideas of what to actually like.
We'll do the same. We'll do it by tonight. Yeah. No, thank you. We'll certainly by tonight we'll get all that together.
So does it mean that we should get prepared for next Tuesday, or we can put a little bit later. That is.
Yeah, probably it'll be Tuesday given like there may be other constraints, right? I mean, I'm fine doing it. No, I think Tuesdays.
I think we'll probably stick to random, but the submission of the proposals later. I don't know if that's your question.
The report itself is not the proposal.
Yeah, the report is 22nd or 23rd, I'm not sure. Like the second day of
because maybe we're still doing some experiments. I'm not sure.
Yeah, but it's a constraint. So that's why I said I'd propose 22nd, but then I realized many are leaving for spring break. There's so many they could have other exams. So I was fine leaving it till later, but due to constraints, we have to.
I mean, you can still mention that it's ongoing work.
Yeah. And anyway, the expectation is all this is still ongoing, right? So, just kind of, it's really like what you did and what's your kind of thinking and again, where it's headed, right? Like kind of just present all of that. Yeah. Thank you. Yeah.